So the question is, I think the components that you just mentioned, I'm pretty sure will be part of the final architecture for AGI. So I think they've come such a long way now, and we've proven out so many things about what they can do. I can't see a world in which we will sort of realize in a couple of years this was a dead end. That doesn't make sense to me. But there still might be one or two things missing on top of what what we already know works. So continual learning, long-term reasoning, some aspects of memory, these are still unsolved. And how to get the systems to be more consistent across the board. I think all of these are going to be required for AGI. Now, it might be that the existing techniques can just scale up to that with some innovation and some incremental innovation. But it could be that there's still one or two big ideas left that need to be cracked. I don't think it's more than one or two, if there are out there. And I think, my betting is about 50-50 if that's the case. It's pretty cool, the dream cycles, and we used to think about this with consolidation with episodic memory. Actually, that's what I studied for my PhD, is how the hippocampus works and integrates, new knowledge gracefully into the existing knowledge base. So the brain does that amazingly well. It does it during sleep, especially things like REM sleep, replaying back episodes that are important so that you can learn from it. In fact, our very first Atari program, DQN, one of the ways it was able to master Atari games was by doing experience replay. So we sort of borrowed that from neuroscience and replayed successful trajectories many times. That's way back in 2013 now, in the dark ages of AI. It was a really important thing. And I agree with you, we're kind of using duct tape right now. So like shove it all in the context window. This seems a bit unsatisfying, right? And actually, even though we're working on machines, not biological brains, and so potentially you could have millions or tens of millions size context window or memory, and it can be perfect. There's still a cost to looking it up and finding the right thing that's actually relevant for the specific decision you've got to make right now. And that's non-trivial, that cost, even if you can potentially store it all. I think there's actually a lot of room for innovation in areas like memory.
Yeah. I mean, the wild thing is it feels like a million token context window is actually bigger than, it's plenty big, honestly. You can do so
Well,
much.
it's plenty big for most things that it should be used for. I mean, if you think about the context window is sort of equivalent to working memory. Humans we have like a few digits. It's like a dozen digits, maybe. Average of 7. We got million or 10 million context windows. But the problem is that we're trying to store everything in that. Things that aren't not important, things that are wrong. It's pretty brute force currently, and that doesn't seem right. And then the problem is if you're now trying to try and process live video, and you're just going to naively record all the tokens, then actually a million tokens isn't that much. It's only like 20 minutes. So actually you need more if you want something that's going to understand your what's going on in your life over maybe a month or two. Yeah, I think potentially it is. It sort of goes in ebbs and waves. We've worked on agents since the beginning of DeepMind. In fact, that's what we said we were working on. So all of the Atari work and AlphaGo, most specifically, they're agent systems. And what we meant by that is systems that are able to, accomplish goals on their own. And make active decisions and make plans. And so, of course, we were doing it in the domain of games to make it tractable, and then doing increasingly complex games, things like StarCraft after AlphaGo, AlphaStar. So we basically did all the games that are out there. And then, of course, the question is, can you generalize those models to be world models or models of language, not just models of simple games or even complex games? And that's what the last few years has been about. But really, you can think of a lot of the things we're doing today, all the leading models with thinking modes and chain of thought reasoning as aspects of what was sort of pioneered with AlphaGo coming back now. And I actually think there's a lot of work we did back then that is relevant today, and we're sort of relooking at some of those old ideas at scale today in a more general way, including things like Monte Carlo tree search and other ways of doing augmenting the RL on top of the reinforcement learning we're ready to do today. And I think a lot of those ideas, both from AlphaGo and AlphaZero, are really relevant to where we are with today's foundation models. And I think a lot of that is what we're going to see of the advances the next few years. I think it's really interesting. I think that's one of the not having continual learning currently is one of the things holding back agents from doing full tasks. I think they're really useful for aspects of tasks right now, and you can patch them together and do some really cool things, but they don't adapt well with the context that you're in. And I think that's the missing piece for them being really kind of fire and forget, and they'll figure it out themselves. I think they need to be able to learn about the specific context that you're going to put them in. So I think we have to crack that to get full general intelligence. There's a lot of innovation left in the thinking paradigms, I would say. Again, I think we're doing fairly simplistic things, fairly brute force. One could imagine, I think there's a lot of scope, for example, in monitoring the chain of thought, maybe interjecting midway through a thought process. I often get the impression with our systems and our competitor systems that they're almost overthinking. They're almost getting into sort of loops of things. Like one thing I sometimes like to do is play chess against Gemini, and it's that all the leading foundation models are pretty poor at games, which is quite interesting. It's very cool to kind of look at the thinking traces, because obviously these can be well understood. I can tell quite quickly if it's going off on a tangent, and it's very sort of provable what the thinking is doing, whether it's useful or not. And so what we see is that sometimes it will consider a move, it will realize it's a blunder, but it can't find anything better, so it kind of goes back to that move and does it anyway. So you just shouldn't be seeing that happening in a very precise reasoning system. So there's just sort of huge gaps, I think, still, but it may only be one or two tweaks that are required to fix those kind of gaps, just to be clear. But I think that's pretty obvious there, and that's why you get this kind of jagged intelligence. On the one hand, it can solve gold medal problems in IMO, which is super hard. But on the other hand, as we've all seen, it can still make basic elementary maths errors if you pose the question in a certain way, right? So, or elementary reasoning errors. So there's just something to me about almost an introspection about its own thought process that I feel like there's something maybe missing there. I think part of it might be, though, that if we want to discuss like creativity, what I often say about that is, like, if we look at the things we've done, like AlphaGo. So obviously, very famously, you'll all know about the move 37 in game 2. And for me, I was waiting for a moment like that to start the science projects like AlphaFold. So we started AlphaFold like the day we got back from Seoul, which is 10 years ago now. I'm going to Korea after this to celebrate the 10-year anniversary of AlphaGo. But it's not enough to come up with move 37. Like, that's pretty cool, very useful, but can it invent Go? That's what I want, a system that can invent Go if you give it a high-level description. Like a game you can learn the rules of in 5 minutes, but it takes many lifetimes to master. It's beautiful aesthetically, but you can play it in a few hours in an afternoon. So, maybe you could imagine that would be the high-level description I would give, and then I'd want the return, the thing I get back is Go. Right. And clearly today's systems, I think, can't do that. So the question is why? And I think there's something still missing there.
Well, someone in this room might make it.
Then the answer would be there's nothing missing. It just was the way we were using the systems. And that might actually be the answer. It might be that our today's systems are capable of that with a brilliant enough creative person using it and providing that impetus, that's the soul of the project, and being able to probably being au fait enough with the tools to like almost be at one with the tools. I could imagine that would be happening if you experimented with the tools all day and all night, like probably many of you are doing that, and you combine that with proper deep creativity. Something more incredible could be done. They're also exciting, and that's why, I mean, that for me has been my main passion and always the reason why I've worked on AI for my whole career for 30 plus years now, is to use AI as the ultimate tool. I always thought AI would be the ultimate tool for science, and to advance scientific understanding, scientific discovery, and things like medicine, and just our understanding of the universe around us. So actually, when you mentioned our original way we used to articulate our mission statement, which is still the way we think about it, is there was two steps to it. Step one was solve intelligence, i.e. build AGI, and then step two was use it to solve everything else. We had to change that a bit over time because people were like, do you really mean solve everything else? And we did mean that, and I think people are sort of understanding what that means today. But specifically, I was meaning solve other, what I call root node problems in science. So areas of science that would unlock whole new branches or avenues of discovery. And AlphaFold is the prototypical example of what we want to do. So over 3 million researchers around the world, pretty much every biology researcher in the world uses AlphaFold now. And I was told by some of my, pharma executive friends that, almost every drug discovered from now on will have used AlphaFold at some point in the drug discovery process. So that's something we're very proud of, and it's the sort of impact that we hope to have with AI. But I do think it's just the beginning. I don't really see any area of science or engineering that this won't be able to be helpful with. And the ones you mentioned, I think we're almost like an AlphaFold 1 moment. So we've got very promising results, but it's not quite solved the grand challenge yet in that domain. But I think we're going to have a lot to talk about in the next couple of years on all those areas you mentioned, materials, which I think is very exciting, all the way to mathematics. The way I should write this up at some point when I have 5 minutes spare, but the lesson I've learned from all the alpha projects we've done, specifically AlphaGo and AlphaFold, is I think the techniques we have and the problems I like to look for are great in if the situation can be described as massive combinatorial search space. The more massive, the better in some ways. So no brute force or special case algorithm will solve it, and that's true of Go moves and of different configurations of proteins far more than the atoms in the universe. Both of those, and then you have a clear objective function. So, you could think of it as minimizing the free energy in the proteins, or, winning the game of Go. So you need to specify your objective function clearly so you can hill climb. And then enough data and or a simulator that can generate you lots of in distribution synthetic data. If those things are true, then I think with today's methods, you can go a long way into tackling and finding the kind of needle in the haystack that you need for the solution that you're trying to look for. And I think of just drug discovery, by the way, in the same way, right? There is a compound out there that would solve this disease if one could find it, if one could only find it, right? And that wouldn't have any side effects and so on. And as long as the laws of physics allows it, then the only question is, how do you find it in an efficient way, in a tractable way? I think we showed for the first time, actually, with AlphaGo, that these systems could find those kinds of needles in a haystack. In that case, the perfect Go move.
How close are we to AI systems that can do genuine scientific reasoning, not just pattern matching on data?
I think we're close. We're working on these general systems like we have this system called Co-Scientist, and we have other algorithms like AlphaVolve that can go a little bit beyond what the basic Gemini will do. And obviously all the frontier labs are experimenting in this way. I've yet to see anything so far, and we all tinker with the same things, some maths problems that are a little bit harder than IMO and so on. I haven't seen anything yet that is a true, genuine massive discovery. That's my personal opinion. I think it's coming. I think it may be related to this thing we discussed about creativity and actually going on beyond the bounds of what's known. So clearly that's just not pattern matching at that point, because there is no pattern to match to, and it's a bit more than extrapolation. It's some kind of analogical reasoning, and I don't think these systems have that, or at least we're not using them in the right way to do that. So the way I often say that in science is, can it come up with a hypothesis that's really interesting, not just solve one? When I say just, we're now talking about just like solving the Riemann hypothesis or something. This would be obviously amazing, or one of the Millennium Prize problems, and maybe we're a couple of years out from doing that. But I'd like to solve P equals NP. That's my favorite one. But even harder than that would be to come up with a new set of Millennium Prize problems that were regarded by top mathematicians to be as, deep and meaningful and worthy of lifetime of study and effort to solve. Right? I think that's another level harder. And we don't have, I still don't think we know how to do that. I don't think it's magical, though. I do think these systems will eventually be able to do that. Maybe we're missing one or two things. And then the way we would test that is, I sometimes call it my Einstein test, which is, can you train a system with the knowledge of cutoff of 1901, and then will it come up with, what Einstein did in 1905, including special relativity, his annus mirabilis? Can it do that, right? And then I think we could run that test. Maybe we should just run that test and keep seeing if that's possible. And once that is, then I think we're on the verge of these systems being able to invent something new, truly novel. Well, there's different things that are hard about each of those things, but I think given life's very short and you only have so much time and energy, you might as well put your life force into something that will really make a difference if you hadn't done it, if you hadn't been there to push it. So I would just think of it through that lens. And then the other thing is, if you are, and then we talked about deep tech, and I love interdisciplinary work, and I think that's going to be even more prevalent in the next few years, in combinations of fields and finding the connections between those fields. And it's going to be even easier to do that with AI. And then the only other thing I would say is, if you have depending on what your AGI timeline is, mine's like 2030 or something like this, then if you start off on a deep tech journey today, usually that you're talking about a 10-year journey for true deep tech, in my opinion. So then now you have to just consider AGI appearing in the middle of that journey. So what does that mean? It's not bad necessarily, but you have to take that into account, right? Will it be able to leverage it? What will the AGI system do with it? And it goes a little bit back to what you said earlier about AlphaFold and general AI systems. So one thing I can see happening is Gemini, Claude, or one of these general systems making use of AlphaFold like specialized systems as tools. I don't think we're going to have it just in one giant brain, because it will have too much regression. If I put all the proteins into, Gemini, that wouldn't make sense. We don't need Gemini to do protein folding. Going back to your information efficiency, it would definitely affect its language skills or something like that, right? In a bad way. So much better, I think, is to have really good general purpose tool usage models that will then, maybe they could even train those specific tools, but they would be in a separate system. So I think that's kind of interesting to think through the implications of that, and then what you might build today. Also physical things too, like what kinds of factories would you build, what sorts of finance systems, and so on. So I just think you need to really take that seriously, in on the one hand is and imagine what that world would look like, and then build something that would be useful if that comes in halfway through.